Hello, and welcome to Lab 1. In this video, I will discuss my observations of an object moving at approximately constant velocity, and model these observations using Newton's second law, also known as the momentum principle. First, I will discuss the physics principles applied in this lab. The first principle is the momentum principle. Change in momentum is equal to net force times change in time. I have rearranged this formula into the form final velocity is equal to net force divided by mass times change in time plus initial velocity. The second principle I will be using is the position update formula. Final displacement is equal to initial displacement plus velocity times change in time. Next, I will discuss the assumptions I have made in this observation and in my model. The first assumption is that the net force is equal to 0. By setting the net force to 0, we eliminate the first term on the right side of the equation, leaving us with final velocity is equal to initial velocity, which is the definition of constant velocity. The second assumption I have made is that the initial velocity is equal to the average velocity near the beginning of my observation. This is a video I made of someone rolling a tennis ball across the floor. I started tracking it a little while after it left the person's hand due to the fact that when it first left their hand, it was accelerating. I set the positive x direction to the left and tracked its motion from frame 41 to 57. This is a graph of the ball's position as a function of time. After making my observation, I collected data from it. First, I measured the mass of the tennis ball and found it to be 0.057 kilograms. Next, I used my earlier assumption that the initial velocity is equal to the average velocity near the beginning of my observation to calculate the initial velocity, which I calculated to be approximately 1.18 meters per second in the positive x direction. The change in time of this observation was 0.533 seconds. The initial position of the ball was the origin. As you can see, I have set the ball's mass to 0.057, the initial position to 0x, 0y, and 0z, and the velocity has been set to positive 1.18 in the x direction. The simulation is set to run for 0.533 seconds. The net force is set to 0, and here you can see Newton's second law. And here is the position update formula. Here you can see a model of the ball's displacement and a graph of its displacement as a function of time. Here is a graph comparing the position of the model and the position of the experiment as a function of time. As you can see, they are very similar. My explanation for the slight difference between the two is the fact that in the experiment, the net force is not quite equal to 0 due to the fact that there is some friction between the tennis ball and the floor, which causes the slight drop in velocity at the end of the experiment when compared to the model. Question: what if you were to flip the axes? As you can see in the model, when I flip the axes by setting the vector to the opposite direction, the only thing that changes is the displacement switches from the positive to the negative direction, along with the slope of the line. Question: can you calculate the pushes and pulls needed to get a net force of 0? Let us think for one moment. In order for an object to have a net force equal to 0, for every external force acting upon that object, there must be an external force of equal magnitude in opposite direction counteracting it. We can use this fact to calculate the pushes and pulls needed to get a net force of 0. This concludes Lab 1, Observation of Constant Velocity and Analysis using Newton's second law.